When you're managing a 140-mile daily commute through the interstate corridors connecting the Midwest industrial belt, Chicago to Milwaukee, Detroit to Cleveland, Minneapolis to St. Paul, you're not thinking about the first 5 years of vehicle ownership. You're thinking about year 10, year 12, the point where most vehicles are supposed to be retired, but yours is still running. That's where the real engineering story emerges. I've spent the last decade analyzing service records from fleet operators, independent repair facilities, and private owners across North America. The data is unambiguous. Some engines reach 300,000 miles with routine maintenance. Others face critical mechanical challenges by 180,000 miles. This isn't random variation. This is engineering philosophy manifesting over time. Let me be clear about what we're discussing today. American manufacturers prioritize different consumer needs, particularly cabin technology, short-term performance metrics, and feature density. Japanese manufacturers have historically prioritized durability and long-term reliability. These are not moral judgments. These are business strategy decisions, and they produce measurably different outcomes in the used vehicle market and at the auction houses across the United States. When you look at the data from the last 10 years of high-mileage vehicle auctions, the resale value gap between a 280,000-mile Honda Accord and a 280,000-mile Chevrolet Impala is approximately 35 to 40%. That gap exists because buyers understand something fundamental. One engine was engineered to reach that mileage. The other was engineered for something else entirely. Today, we're exploring why. Let's begin with a technical truth that most vehicle owners never consider. An engine's maximum lifespan is determined by heat management. Combustion temperatures inside the cylinder reach 2,500 degrees Fahrenheit. The engine block, cylinder head, pistons, valve seats, and gaskets experience continuous thermal cycling, thousands of heat cycles per minute. The margin between normal operating temperature and material degradation is where longevity is actually engineered. Japanese manufacturers, particularly Toyota and Honda, approach cooling system design with what I call conservative thermal architecture. Let me explain what that means in measurable terms. Larger heat exchange capacity. A Toyota 5.7-liter V8 engine, found in Sequoias and Tundras, used extensively on Midwest commuting corridors, uses a radiator with approximately 18% greater cooling surface area compared to a comparable displacement American V8. That's not accident, it's specification. The water pump displacement is higher. The thermostat opens at 82 degrees Celsius instead of 90 degrees. The cooling fan engagement threshold is lower. All of this creates a system designed to keep the engine operating at 195 to 200 degrees Fahrenheit under sustained load, rather than the 210 to 220 degree range common in American engines. In my experience reviewing service logs from regional fleet operators managing high-mileage vehicles, this 2-decade temperature differential compounds dramatically. Vehicles operating at lower sustained temperatures show significantly lower rates of head gasket degradation, valve seat recession, and bearing wear. A Toyota Sequoia with 260,000 miles typically shows minimal head gasket deterioration. A comparable Chevrolet Suburban at the same mileage frequently requires gasket service. Material science and thermal conductivity. Japanese manufacturers use different aluminum alloy compositions in their engine blocks. The 2GR-FE engine block, Toyota's 3.5-liter V6, engineered for durability and commonly found in vehicles exceeding 250,000 miles, uses an A356 aluminum alloy with specific thermal properties. This alloy distributes heat away from critical surfaces more effectively than the comparable AL-SI alloy used in many American applications. What does that mean practically? Heat dissipation. When the piston crown is subjected to 2,500 degree combustion temperatures, that heat must travel through the piston material and into the cylinder wall, where the cooling system removes it. Better thermal conductivity means faster heat transfer, lower peak temperatures at critical surfaces, and slower material degradation. When you examine cylinder walls using borescopes at 200,000 plus miles, Japanese engines show significantly less taper and less crosshatch pattern degradation. American engines show greater wear rates, not catastrophic wear, but measurable wear that compounds at extended mileage. Turbocharging philosophy. Here's where manufacturing strategy becomes explicit. American manufacturers increasingly use turbocharging and aggressive boost pressure to meet performance and efficiency targets. A turbocharged four-cylinder produces the horsepower of a naturally aspirated six-cylinder while improving fuel economy. This is excellent for marketing metrics and EPA ratings, but turbochargers introduce sustained heat stress. Turbine inlet temperatures exceed 900 degrees Celsius. The turbo itself operates at 150,000 plus revolutions per minute. That's thermal and mechanical stress that doesn't exist in naturally aspirated engines. Japanese manufacturers have largely avoided turbocharging in their high-volume models destined for long-term ownership. A Honda Accord uses a naturally aspirated four-cylinder or six-cylinder. A Toyota Camry uses naturally aspirated four-cylinder or six-cylinder architecture. This conservative approach trades performance metrics for durability. An engine that operates at 5,000 revolutions per minute maximum under load will experience less thermal stress than an engine operating at 6,500 revolutions per minute under equivalent load. When you review service data from vehicles exceeding 250,000 miles, naturally aspirated Japanese engines dominate the longevity statistics. Turbocharged American engines show significantly higher rates of critical component failure at extended mileage. Transmission longevity is where design philosophy becomes brutally clear in real-world data. Japanese manufacturers, Honda, Toyota, Mazda, approach transmission engineering with redundancy. Stronger internal components, more conservative gear ratios. Transmission fluid specified for extended drain intervals, some rated for 100,000 plus miles without fluid change. American manufacturers have prioritized efficiency and performance. Tighter gear tolerances, more aggressive gear ratios, thinner transmission fluids for lighter weight and lower parasitic drag. CVT transmission realities. Here's a critical technical distinction. Nissan, Japanese ownership, American manufacturing strategy, uses continuously variable transmissions extensively in North American models. Honda and Toyota use CVTs selectively with heavier reinforcement. In my experience reviewing fleet maintenance records, Nissan CVTs show significant performance degradation between 110,000 and 140,000 miles. Hesitation, shuddering, delayed engagement. Toyota CVTs in equivalent age vehicles, say a 2015 Corolla with 180,000 miles, show minimal performance change. The difference is internal construction. Toyota's CVT uses heavier pulley systems, stronger chain construction, and transmission fluid with better thermal stability. Nissan's CVT prioritizes weight reduction and cost efficiency. Does this make Nissan's approach wrong? No, it's a business decision. Nissan prioritizes meeting 4-year lease return targets. Toyota engineers for 15-year private ownership. Traditional automatic transmissions. When you examine traditional 8-speed and 10-speed automatics, the pattern repeats. Japanese transmissions, Honda's 10-speed, Toyota's 8-speed, are engineered with greater internal clearances and less aggressive shift programming. American transmissions, Ford's 10-speed, General Motors' 10-speed, use tighter tolerances and more dynamic shift mapping. Tighter tolerances mean better fuel economy and sharper performance initially. But at 200,000 plus miles, they also mean greater internal wear rates and higher friction losses as components wear. In high-mileage auction data across the Midwest, Japanese automatic transmissions show dramatically lower failure rates beyond 200,000 miles. This is measurable through transmission temperature readings, shift quality assessments, and actual failure statistics. Transmission fluid specification. American manufacturers typically specify Dexron or Mercon automatic transmission fluids, rated for conventional service intervals of 30,000 to 50,000 miles. Japanese manufacturers specify fluids with greater thermal stability, often rated for 100,000-mile drain intervals. When you calculate total transmission stress over 300,000 miles, this difference is significant. The fluid in an American transmission is changed 6 to 10 times. The fluid in a Japanese transmission might be changed 2 to 3 times. Less fluid degradation, less contamination, less stress on the hydraulic system. This is where precision engineering becomes visible in metallurgy and manufacturing specification. Bearing and journal surface quality. Japanese manufacturers specify tighter tolerances on crankshaft and connecting rod bearing journals. A Toyota engine's crankshaft is polished to a surface roughness specification of 0.4 micrometers RMS. Comparable American applications often specify 0.6 to 0.8 micrometers. This difference affects oil film thickness and bearing wear rates. Smoother journal surfaces support more stable oil films at extended mileage. At 200,000 plus miles, this compounds into dramatically different wear rates. When you perform wear metal analysis, testing used oil for iron, copper, aluminum content on high-mileage engines, Japanese engines show significantly lower wear metal concentrations. That's not opinion, that's chemistry. Valve material and hardness. Japanese engines use hardened intake valves, nitrided or coated surface hardness, exceeding 900 HV. American engines historically used standard hardened valves, surface hardness 700 to 800 HV. Harder valve surfaces resist wear from combustion gas pressure and valve seat contact. Less wear means longer valve life and better sealing at extended mileage. Casting quality and porosity control. Japanese foundries implement stricter porosity control in aluminum casting. Fewer gas pockets, better grain structure. This affects the internal structural integrity of engine blocks and heads. American foundries prioritize cost efficiency, which sometimes means accepting higher porosity rates. A pinhole in an engine block at 180,000 miles might not cause catastrophic failure, but it affects long-term integrity and cooling system stability. When you examine used engine blocks at salvage yards, Japanese blocks, even at 200,000 plus miles, show significantly fewer cooling system seepage points. American blocks at the same mileage frequently show minor weeping around core plug areas. Let me make this tangible by connecting engineering decisions to actual dollars. A 2015 Honda Accord with 210,000 miles currently resells for approximately $12,800 at U.S. auction houses across the Midwest. A 2015 Chevrolet Cruze with identical mileage resells for approximately $8,200. That's a $4,600 gap, 35% higher resale value for the Japanese engineered vehicle. Why? Because buyers and auction operators understand something fundamental. The Honda is likely to reach 280,000 miles with routine maintenance. The Chevrolet faces higher probability of significant mechanical issues before 250,000 miles. When you calculate total cost of ownership over 15 years, purchase price difference, $2,000 to $3,000. Japanese typically costs slightly more. Resale value advantage, $4,000 to $6,000. Japanese holds value significantly better. Maintenance cost difference, $1,500 to $2,500. Japanese typically costs less. The Japanese vehicle costs approximately $2,000 to $4,000 less to own over 15 years, despite a higher initial purchase price. This isn't abstract. This is why high-mileage commuters in the Midwest, especially those managing 80,000 to 100,000 miles annually, systematically choose Japanese vehicles. The long-term economics are compelling. Conclusion: choosing for the long term. Here's what the engineering data tells us. Longevity is not accidental. It's designed. Japanese manufacturers have made explicit engineering choices. Conservative thermal design, naturally aspirated engines, robust transmission architecture, stricter material specifications, higher manufacturing tolerances. These choices cost money. They trade short-term performance metrics for long-term durability. American manufacturers have made different choices. Efficient cooling systems, turbocharged engines, cost-optimized transmissions, tighter tolerances, lighter construction. These choices deliver better initial performance, better EPA ratings, and lower manufacturing costs. But they produce different long-term outcomes. If you're purchasing a used vehicle for a high-mileage daily commute, especially in the Midwest corridors or on Interstate 80, 90, or 94, where 80,000 plus annual miles are common, the engineering differences matter profoundly. A Honda or Toyota with 180,000 miles might have another 120,000 plus miles of reliable service ahead. A comparable American vehicle at the same mileage might face critical mechanical challenges within 40,000 miles. When you're facing a 6-year ownership cycle and high annual mileage, that engineering difference becomes your actual cost of ownership. The longevity gap isn't a secret. It's engineering, and it's measurable in service logs, auction prices, and the reliability records of thousands of high-mileage vehicles across the United States. Choose accordingly.